Consider the apple you might have on your desk. It contains around 100 million cells and about 10 to the power of 25 individual atoms. Each atom measures no more than a nanometer across. If we consider the absolute maximum number of things you could pack inside an apple, measured in the smallest conceivable cubic unit known as a Planck volume, that number is roughly 10 to the power of 102. Scaling up, you could fit roughly 100 apples into the volume of an average person, and about 10 to the power of 25 apples inside the volume of Earth. Approximately 10 to the power of 66 apples could fill the Milky Way galaxy, and around 10 to the power of 84 would occupy the entire observable universe. This places both you and the apple at a unique nexus, a point where competing cosmic forces, interactions, and laws reach a kind of equilibrium. The apple represents a balance point in the scale of the universe. At about 10 centimeters across, it is roughly 35 orders of magnitude larger than the Planck length, the smallest meaningful measure of distance, and about 27 orders of magnitude smaller than the observable horizon of the cosmos. This means 62 orders of magnitude separate the smallest from the largest scales we know, a number that describes the entire cosmos and everything within it. While this may seem random, the apple sits precisely at the midpoint between these extremes, at the center of the universe's scale. Understanding why it occupies this precise balance point may hold the key to explaining why the cosmos exists in the first place. In 2013, NASA's K-10 rover was undergoing tests at the Ames Research Center in California. Astronauts aboard the International Space Station remotely controlled its movements and science operations using a laptop interface and live data links. This remarkable achievement demonstrated the potential for humans to command robots on distant worlds like Mars or the Moon from orbit. The ability to control technology remotely is incredibly useful, not just in space, but across the globe. For anyone needing to access a computer from afar, for personal or business purposes, there are tools designed specifically for this task. One such tool offers fast remote access, making it feel as if you are sitting right in front of the distant machine. It's excellent for tasks like video and audio editing when away from a primary workstation, and is very effective for transferring large files directly and securely, bypassing cloud services entirely. This is ideal for moving high-quality footage or entire documentaries between team members and has numerous applications for various projects and businesses. It is compatible with all major platforms, works with older operating systems, and boasts exceptional reliability. Best of all, personal use is completely free, with tailored plans available for teams and businesses. This premium remote access tool is available for anyone to try at no cost. When Max Planck began his university studies in 1875, he asked his respected teacher, Philip von Jolly, for advice on the state and future of his chosen field. His teacher described physics as a highly developed, nearly mature science, suggesting theoretical physics was approaching completion, much like geometry had centuries before. 25 years later, to his former mentor's astonishment, Planck would revolutionize this supposedly mature field, and he did so almost by accident. Planck was eager for a physics education, but found his lectures stuffy and old-fashioned. He considered his professors, Hermann von Helmholtz, disorganized and Gustav Kirchhoff dry, so he largely taught himself, the perfect recipe for a revolutionary. At the close of the 19th century, Planck tackled what von Jolly would have considered one of physics' final puzzles, mathematically describing the spectrum of radiation emitted by hot objects, like a metal poker pulled from a fire. Genius after genius had tried and failed. There's a saying that there are two kinds of physicists, those who play by the rules and those who get physical constants named after them. Planck persisted. After exhausting all conventional approaches, he introduced what he called a mathematical trick. Instead of assuming light was emitted in all possible amounts, he proposed that hot objects could only emit discrete chunks, or quanta, of radiation. To describe the smallest possible chunk of light, he introduced a special number, a constant. With this, the unstoppable fire of a scientific revolution was lit. By Planck's time, physicists were accustomed to constants. Some were artificial, standardized measurements like the meter or the ounce. Others seemed to emerge from nature itself, like Newton's gravitational constant or the speed of light, values with no deeper explanation. They simply were. However, no constant had ever described something as incredibly tiny as Planck's quantum of light. The most precise measurements of the era were on the scale of microns, allowing scientists to study bacteria and cell structures. Planck's constant operated far, far beyond that realm. 626 times 10 to the power of negative 34 joule-seconds dictates where and when quantum effects dominate, where the certainties of our familiar world dissolve into probabilities and uncertainties. Planck combined this constant with three others: the speed of light, Newton's gravitational constant, and Boltzmann's constant, to create a set of reference points for the quantum world, the Planck units. These include a Planck time of about 10 to the power of negative 44 seconds, a Planck energy around 10 to the power of 9 joules, and a Planck length of about 10 to the power of negative 35 meters. These units tell us that any object, system, or event approaching these limits will be governed by quantum mechanics. What happens at these extremes remains a mystery. They appear to be the universe's fundamental limits. Beyond them, quantum chaos reigns, and our current mathematics cannot describe it. Fortunately, we are unlikely to encounter these limits soon. The world's most powerful particle accelerator, the Large Hadron Collider, achieves collision energies of 14 tera-electronvolts. If a tennis ball carried that energy, it would shine as brightly as 100,000 Hiroshima explosions. 2 times 10 to the power of 20 electron volts, over 40 million times more powerful than collisions in the LHC. The Planck energy is nearly 40 million times more energetic than even that. In 2020, German scientists shot X-rays at a hydrogen molecule. A photon bounced off one electron, scattering it away, then ricocheted to a second electron, freeing it. The two electrons interfered with each other. By measuring this interference pattern, scientists deduced the time it took for the photon to travel between the electrons, 247 zeptosecond, the shortest time interval ever measured. A zeptosecond is a trillionth of a billionth of a second. The Planck time is another 23 orders of magnitude shorter. Meanwhile, attempts to measure the size of an electron by trapping it show it must be no larger than 10 to the power of negative 22 meters, the smallest direct measurement ever made. The Planck length is 1,000 billion times smaller than that. The world of the Planck scale remains hidden from modern science, even with our most advanced instruments. However, quantum field theory offers some insights into what might occur at these unimaginably small scales. In 1941, Werner Heisenberg made a trip that would alter his career, visiting his longtime friend and mentor, Niels Bohr, in Nazi-occupied Copenhagen. During their conversation, Heisenberg raised the topic of nuclear weapons. His intentions remain unclear. Bohr, understandably, assumed Heisenberg was attempting to recruit him for the Nazi atomic bomb project and was horrified. They parted on uncertain terms and never spoke directly again. The details remain ambiguous. Heisenberg insisted his goal was not recruitment and that Bohr misunderstood. His work during World War II is similarly ambiguous. While he worked for the Nazis on nuclear research, he always maintained he deliberately slowed the project, a fittingly uncertain legacy for the man who introduced uncertainty to the quantum world. Decades earlier, during the quantum revolution of the 1920s, Heisenberg proposed something utterly foreign to the macroscopic world. His uncertainty principle stated that it is impossible to measure both the position and momentum of a particle with infinite precision. Measuring one property precisely means sacrificing knowledge of the other. While Heisenberg initially framed this in terms of measurement disturbance, later work showed it was a fundamental fact of nature, like gravity or the constant speed of light. The number governing this trade-off is none other than Planck's constant, the ultimate arbiter of the quantum realm. Heisenberg's principle implies that the quantum fields permeating spacetime are never completely still. Even in a vacuum, these fields possess a fixed amount of residual energy, a ground-state vibration. At the Planck scale, these vibrations cause spacetime itself to distort beyond recognition. At our familiar macroscopic scales, far above the Planck length, spacetime is smooth, like a thin rubber sheet. It may have dips, hills, and ripples, but it remains unbroken. However, the inherent uncertainty in quantum fields causes energies to fluctuate and particles to pop in and out of existence, allowed by uncertainty, as long as they vanish quickly enough. This energetic chaos causes spacetime to bend and flex in response. This is the concept of quantum foam at the Planck scale, around 10 to the power of -35 meters. It is the fundamental substrate of reality at the smallest distances, a seething region where tiny twists and whirls of spacetime appear and vanish, with momentary wormholes connecting one pocket of space to another. We have no way to describe reality at these scales. Einstein's general relativity demands smooth spacetime, while quantum field theory says it is not. The Planck scale is so minute that many scientists doubt whether our current understanding of physics or even reality can ever make sense of it. To grasp this, consider a film. Movies aren't truly continuous. They are a series of still images played at 24 frames per second. Our perception blends them into smooth motion. But if you could perceive each individual frame, the illusion of continuity would shatter. Is time quantized at the Planck scale? Does our sense of continuous time break down? What about space? We perceive motion as fluid, not a series of staggered snapshots. Are our perceptions deceiving us? We've measured incredibly brief intervals of time and tiny displacements in space, but we cannot come close to the Planck scales. So what is happening down there? Do time and space exist in any meaningful way? If not, how does the structure of the universe arise? The apple might offer a clue. The weakest known force interaction is the weak nuclear force, with a range of only 10 to the power of -18 meters. An object at the Planck scale would be far smaller and would experience the weak and strong nuclear forces, electromagnetism, and gravity, all combined and equally potent. Such conditions were last seen in the universe's first moments after the Big Bang. At Planck scales, physicists believe all forces of nature merge into a single, unified force, though its nature remains unknown. So what becomes of an apple compressed to the Planck scale? According to our best theories, it would collapse into a singularity, a point of infinite density. However, in the speculative theory of loop quantum gravity, spacetime is discrete and quantized at the Planck scale. This theory posits a smallest possible size, a pixelation of spacetime that prevents further compression. Perhaps the apple would become stuck at this smallest unit, experiencing forces and energies beyond our current science, with a direct view of the quantum foam that permeates the cosmos. Thankfully for the apple in our snack, an apple is vastly larger than the Planck scale. Over a trillion Planck lengths could fit side by side across its diameter. It exists in a realm so far removed from the quantum chaos that it might as well be a different universe. But there is a bridge between the Planck scale and the apple. To build macroscopic objects, you need atoms. When discussing atoms, language can only be used as in poetry. Experimenters carefully calibrated a laser, targeting a single hydrogen atom chilled to nearly absolute zero. Their goal was to take its picture, an idea first proposed in 1981 by Russian theorists, finally realized in 2025. The method involved hitting the atom's electrons so they scattered, then measuring their velocities to reconstruct their original positions. Repeated many times, these measurements built up a portrait of the atom. The result was bizarre, a series of overlapping rings, clusters, and gaps. They were not mapping the electrons themselves, but the waves of probability describing where the electrons might be. Each laser pulse encountered the electron in one particular position, sometimes here, sometimes there. Where the probability waves crested indicated where the electron was most likely to be found. The gaps showed where it never appeared. An atom is roughly 100,000 times larger than an electron, and about 10 to the power of 25 times larger than the Planck length. Even at these subatomic scales, we are unimaginably far from the universe's deepest structures. Why is an atom this specific size? Why are all atoms of the same element identical across the cosmos? It's as if every skyscraper in a city were exactly the same. There must be something universal and fundamental about them. The 2025 image of a real atom differs greatly from popular depictions of a central nucleus with orbiting electrons. That iconic symbol is everywhere, even standing in for science itself, but it is inaccurate and outdated. It represented the first modern attempt to understand atomic structure, created by a man whose own start was not particularly promising. The young Niels Bohr, who would become Heisenberg's mentor and later estranged friend, was not adept in the chemistry lab. He had a fondness for mixing chemicals that shouldn't be mixed, leading to frequent explosions and a reputation for breaking glassware. It was better for everyone when he turned to theoretical physics. At the dawn of the quantum revolution, Bohr was drawn to two ideas: Max Planck's concept that certain quantities come in discrete lumps, and the work of his mentor Ernest Rutherford, who discovered the atom's small, dense, positively charged nucleus. Bohr wove these strands together to create the first quantum model of the atom. At its center was the nucleus, a compact ball of positive charge. But what of the electrons? Other scientists imagined a plum pudding of spread-out negative charge. Bohr replaced that with mostly empty space. He conceived of electrons as particles held by electrostatic attraction to the nucleus. But this should cause collapse. Bohr turned to quantum mechanics for a solution. Electron orbits were quantized. Unlike planets, which can have any orbit, electrons could only occupy specific, discrete orbits. For a hydrogen atom, the closest an electron can approach is the Bohr radius, roughly 10 to the power of 24 Planck lengths. The nucleus itself is typically only a few femtometers across, about 10 to the power of 20 Planck lengths. 99,999,999% empty space, their size governed by the balance between electrostatic forces and the quantization of angular momentum. Bohr's model was a first step. Later, Erwin Schrödinger discovered why electrons were confined to these orbits, inspired by Louis de Broglie's suggestion that matter, like light, could have wave-like properties. When you pluck a guitar string, the vibration is quantized because the ends are fixed. Schrödinger envisioned the electron's matter wave wrapping around its orbit like a string. The orbit was quantized because the wave had to fit perfectly. This is what the 2025 experiment revealed, not electrons, but the probability waves that describe them. This is key to understanding the atomic world. These waves are not physical like ocean waves or sound waves. Schrödinger initially thought matter smeared out across space, but he was wrong. Quantum waves are probability waves. They describe where a particle is likely to be found. Where the wave crests, the chance of finding the particle is high. Where it shrinks, the chance is low. The subatomic world is profoundly different from our macroscopic reality. The closer you get to Planck scales in size, time, or energy, the more the wave nature of reality manifests. The farther away you are, the more these waves are suppressed, though this line is drawn at much larger scales than once thought. The largest object shown to demonstrate measurable wave-like behavior is a molecule containing around 2,000 atoms. While quantum mechanics moved beyond Bohr's initial model, he was right about one crucial point. Atoms exist with their specific properties due to the intersection of fundamental forces. If you could fly a tiny ship inside an atom, you'd see mostly empty space filled with vibrating quantum fields. The nucleus would be a tiny, dense point. The electrons wouldn't be little balls. They'd be invisible probability waves that only give a definite location when observed. It is the electromagnetic force competing with quantum rules that gives rise to the Bohr radius and electron orbits. Deep inside the atomic nucleus, another set of forces compete. Atoms are not simple. Their nuclei are bundles of protons and neutrons. Neutrons are electrically neutral. Protons are positively charged. They are exceptionally close together, less than a few femtometers apart. At that distance, the electrostatic repulsion between protons is about 50 newtons, enough force to lift a watermelon. Applied to something as tiny as a proton, this force should blow the nucleus apart. Yet, it doesn't. Why? In 1934, at Osaka Imperial University in Japan, 26-year-old Hideki Yukawa was fixated on this mystery night after night. He had tried dozens of approaches without success. Unable to turn to experiments, he relied on theory. One late night, clarity struck. He proposed a new force of nature, carried by a massive particle, that resisted the electric repulsion and kept the nucleus stable. What Yukawa started that night changed our understanding of atoms, though he didn't grasp its full significance at the time. "Once I published my paper," he later said, "I felt like a traveler who rests himself at a small tea shop at the top of a mountain slope." We now call this force the strong nuclear force. Pulling a proton or neutron from a nucleus requires working against it, like resisting gravity to lift an object from Earth. This means energy is stored in every atomic nucleus. All nuclear power, from city-leveling bombs to the reactors powering homes, is based on extracting this energy. If we could harness the nuclear binding energy in a sandwich, it would yield an explosion comparable to several megatons of TNT. Yet in the modern picture, this nuclear binding isn't fundamental. It's an accident, because protons and neutrons aren't fundamental either. They are composed of even smaller particles called quarks. To understand quarks, we enter a place of scientific worship. The central twin spires rise gracefully like a modern Tower of Babel. This spectacular edifice, designed to emulate a French Gothic cathedral, is surrounded by sculptures: a 21-ton arch depicting broken symmetry, a Möbius strip, a hyperbolic obelisk. This is Fermilab, a particle accelerator outside Chicago. In 1995, here at Fermilab, the last building block of the subatomic universe clicked into place. Two teams working with the Tevatron, then the world's most powerful particle collider, finally found what they had sought for 2 decades: the top quark. The top quark had eluded detection due to its enormous mass, over 170 million electron volts, about 180 times heavier than a proton. This huge mass requires immense energy to create and makes it incredibly unstable, vanishing almost instantly. This particle is the king of quarks, dwarfing the other 5: the bottom, strange, charm, up and down quarks. Quarks are governed by the strong force, which binds them through the exchange of gluons. This force is so powerful that individual quarks are never seen alone. Trying to separate two quarks requires so much energy that new particles, including other quarks, pop into existence between them, immediately binding to the ones being pulled apart. The discovery of the top quark solidified our understanding of the atomic hierarchy and why atoms have their specific properties. Imagine an apple the size of an atom. Why does its nucleus shrink to a femtometer, and why does the nearest electron sit a nanometer away? Nature builds from stable foundations, from entities that can persist. Atoms exist at the confluence of the strong and electromagnetic forces and the ironclad rules of quantum mechanics, where a balance is struck between all three. There are 6 types of quarks, but the most massive ones destroy themselves before building anything larger. This leaves the lightest ones, the up and down quarks, to create matter. Bound by the strong nuclear force, they form protons and neutrons. The gluons carrying the strong force have mass, giving them a limited range of less than a femtometer. However, some residual strong force leaks out, easily overwhelming the electrostatic repulsion between protons, but only over very short distances, up to a few femtometers, before the electric force takes over. This crossover point determines the size and shape of the atomic nucleus. The largest known element, oganesson, has 118 protons spanning over 1,000 femtometers, sitting at the limit before electrostatic repulsion tears the nucleus apart. Similarly, while electrons have heavier, unstable cousins, only the lightest electrons survive long enough to participate in larger structures. The electron feels the nucleus's attraction, but is prevented from collapsing into it because its wave function can only be compressed to a certain limit. This is how an atom forms, From the quantum chaos of the Planck scale emerges a zoo of particles and forces. Certain particles have properties that allow them to build structures far larger than the Planck length. In this way, an atom is built like a bustling city of quantum activity. Yet, a question remains: why do subatomic particles like quarks and electrons have their specific masses and sizes? This is one of the great mysteries of modern physics. Like explorers in an unknown jungle, physicists sometimes must simply observe and record, leaving true understanding for future generations. But this is not the end of the story, nor the end of the structures that assemble at larger scales. More forces and convergences make much larger objects possible. Atoms with consciousness, matter with curiosity, stands at the sea, wondering. The Tribut River flows through a desert, cutting a green swath against the flat-topped mesas of northern Patagonia. In 2010, a ranch hand named Aurelio Hernandez stumbled upon a strange-looking outcropping. Thinking it was a rock, he brushed away the soil and kept brushing, eventually unearthing a fossilized bone almost 8 feet long. Over the next few years, paleontologists uncovered more than 200 fossils at the site, including one of the largest creatures ever to live. They are called titanosaurs. You can see one named Maximo at the Field Museum in Chicago. It stretches 122 feet from head to tail and stands 28 feet tall at the head. It lived over 100 million years ago, and when it walked, the ground quaked under its 70-ton weight. Maximo is one of the largest creatures ever, but it doesn't hold the crown. The largest living fungus is found in the Malheur National Forest in Oregon, 4 square miles, and is over 2,000 years old, with an estimated weight exceeding 35,000 tons. As for the smallest, while virus's status is debated, bacteria unquestionably count as living. The smallest known free-living bacteria is Pelagibacter ubique, a ubiquitous oceanic bacterium only a few hundred nanometers long. Despite its minuscule size, this species is so numerous that its total mass outweighs all the fish in the world's oceans combined. Life spans an immense size range. The leap in size from a bacterium to the Malheur fungal colony is far greater than that from an atom to a bacterium. At the scale of life, truly bizarre physics begins to emerge. At the smallest scales, between the Planck length and simple life, the universe obeys relatively straightforward physical laws. Forces act over certain distances, and particles respond. However, no equation in physics predicts how a bacterium consumes food or how a blue whale sings. Between the laws of nature and biological systems lies not just many orders of magnitude, but an unimaginable leap in complexity. This is the concept of emergence, how simple rules can lead to surprisingly complex behaviors. The best illustration is a game. Imagine a grid of cells, then apply these rules. Any live cell with fewer than 2 live neighbors dies, underpopulation. Any live cell with 2 or 3 live neighbors lives on. Any live cell with more than 3 live neighbors dies, overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell, reproduction. This is the game of life, created by mathematician John Conway and featured in Scientific American in 1970. It shows how complexity arises from simple rules. 2 games with only slightly different starting arrangements can lead to wildly different patterns, structures, and behaviors emerging dozens of iterations later. Conway's game of life is Turing complete, meaning with sufficient preparation, it can act as a fully programmable, general-purpose computer. Anything your smartphone can do could, in principle, be done with a large enough game of life grid. Emergence isn't just a property of games, it's found everywhere. The world is governed by fundamental laws, but that doesn't mean we can use those laws to describe everything. Each bird in a flock follows simple rules, yet the flock's movement is unpredictable. No single ant knows how to build a colony, yet a colony emerges when many ants gather. It's not just life. Individual hydrogen and oxygen molecules aren't wet, but wetness emerges from countless interactions among trillions of molecules. Scientists believe our conscious experience is rooted in nature's fundamental forces, yet we cannot explain consciousness itself. At some point billions of years ago, molecules made the leap from inorganic to organic, an emergent leap that still defies easy explanation. A single living organism, even a bacterium, is perhaps the most complex structure in the universe, with information, energy, and interactions spanning 10 orders of magnitude in scale. This is our scale, the scale of humanity, dominated by the electromagnetic force. Electromagnetic attraction and repulsion, the sharing of electrons as wave functions overlap. This force binds electrons to nuclei and atoms to each other. It pushes, pulls, repels, draws, and mixes. Atoms become molecules, molecules become compounds, compounds become living tissue. A sodium ion crossing a neuron's membrane involves electromagnetism. Your heart beating faster involves electromagnetism. The touch of a lover's skin involves electromagnetism. Electromagnetism also sets limits on the size of living creatures. The smallest organisms must be complex enough to perform life's basic functions: reproduction, nutrient gathering, requiring a minimal number of atoms and molecules. For the largest creatures, electrical and chemical nerve signals can only transmit information so quickly. This is why giant sequoias and fungal colonies can be far larger than Maximo the dinosaur or the largest blue whales. They don't need to move or react in real time. Even among these, electromagnetism sets a limit through heat. Every cell captures, stores, and releases energy, each process generating a tiny amount of heat. With 30 to 40 trillion cells in the human body alone, every creature must manage heat. This is why large animals like elephants have large ears and little hair to radiate heat. The largest possible land animal is estimated at around 120 tons, just a bit larger than Maximo, for this very reason. All of life, mediated by electromagnetism, operates at a scale so important we defined our common measure by it. Centuries ago, measurements were based on everyday experience. A foot was roughly the length of a human foot, divided into 12 inches for easy fractions. An acre was the land a farmer and oxen could plow in a day. The French Revolution sought a system based on reason and science. The French Academy of Sciences devised the meter, defined as 1/10,000,000th of the distance from the North Pole to the equator along a meridian passing through Paris. In 1983, this definition was revised. A meter is the distance light travels in a vacuum in 1/299,792,458 of a second. The meter was now tied to a fundamental constant, the speed of light. With this definition, we measure the cosmos down to the Planck scale. A single Planck length must be multiplied almost a billion times to reach a meter. All of life exists within a range from nanometers to tens of meters. Peering into an apple reveals the dazzling complexity of life's machinery contained within those scales. Each cell is a bustling biochemical metropolis. Its defensive walls are a cuticle of fatty acids. Its government office is the nucleus, home to DNA. Its police, firefighters, and engineers are proteins and enzymes that fix, repair, break down, rebuild, and ward off invaders. Its power plants are mitochondria, converting sugar into energy, or chloroplasts, turning sunlight into sugars. Everything within an apple's cell is governed by electromagnetism, and at the smallest scales, the strong and weak nuclear forces. But that's only 3 of the 4 fundamental forces. At far larger scales, bigger than the largest living creatures, gravity comes into its own. It's time for a road trip across the surface of the sun. Our craft leaves the northern polar regions heading south at 70 miles per hour, an average commute speed. The poles are regions of intense activity where magnetic fields twist, wind, and plunge into the surface, accompanied by convulsions of plasma. Mountains of plasma half the size of a planet rise and collapse within hours. Soon, we encounter our first granule, a chunk of erupting solar material spanning about 1,500 kilometers. Crossing it will take most of a day. After a few days, we reach a sunspot, a massive cavity where immense magnetic fields punch through the plasma, creating a chasm 1,000 kilometers deep. This medium-sized one is just over Earth's width. At our speed, crossing it would take a few days without stops. As we crawl on, we see prominences and flares, great arching structures where magnetic fields funnel stellar material into space. These eruptions are unpredictable, stretching 1,000,000 kilometers or more before falling back, volumes so vast they could cradle all the planets of the solar system. We've barely started. At this pace, reaching the sun's equator, a quarter of its circumference, would take over a year. Best to bring a snack. Ancient people believed the sun and moon were the same size. In a sense, they are. By cosmic coincidence, the sun is roughly 400 times wider than the moon, and also about 400 times farther away. This makes Earth the only planet with perfect total solar eclipses. Even from 150 million kilometers away, the sun's power is enough to melt ice in your drink on a summer afternoon. Thankfully, the vast vacuum between us blocks sound. If it didn't, the sun's noise would be louder than a jet engine at takeoff every second of every day. The sun is by far the largest object in the solar system. It is the solar system. All planets, including Jupiter, are mere rounding errors compared to its mass and radius. The sun contains 99% of all material in the system. 1,000,000 Earths could fit within its volume. Even mighty Jupiter only slightly nudges the sun as it orbits. The sun is roughly 10 to the power of 44 Planck lengths across. Earth is about 10 to the power of 42. Why is the sun so much larger? As with all previous layers, the answer lies at the intersection of competing forces. In Sudbury, Ontario, Canada, over 2,000 meters underground in an unused mineshaft, sits a strange piece of technology. No sunlight reaches here. The temperature is a sweltering 50 degrees Celsius from surrounding rock. At the center of an empty chamber is what looks like a cosmic egg. Built by astronomers, this instrument had no mirrors or lenses. It couldn't see the sky, but it could peer into the sun's heart. Activated in May 1999, it was the Sudbury Neutrino Observatory. The observatory consisted of a geodesic sphere holding 1,000 tons of heavy water, donated by Atomic Energy of Canada Limited, worth over $330 million at the time. Mounted on the sphere were 96 photo-multiplier tubes to amplify any faint light within the water. For 7 years, it watched as ghostly particles streamed through it. It was built to solve a decades-old solar mystery. At the dawn of the nuclear age, physicists realized fusion powered the sun. Every fusion reaction produces a neutrino. Hundreds of trillions pass through your body every second. But previous experiments detected only about 1/3 of the expected neutrinos. Did this mean the sun was 2/3 smaller? No, the answer lay in the neutrinos themselves. Previous experiments could only detect one flavor. The Sudbury Neutrino Observatory could measure one flavor and the total number simultaneously. After years of analysis, it demonstrated that neutrinos change flavor as they travel. This discovery rocked physics, creating the mystery of neutrino oscillation that persists today. It also confirmed that fusion, and fusion alone, makes the sun shine. Every minute, the sun fuses an Earth's worth of hydrogen into helium at its core, at temperatures around 10 million Kelvin. Each conversion releases a little mass as energy. Multiplied countless times, the sun produces more energy in 1 second than humanity uses in 100,000 years. The sun's massive weight creates an immense gravitational pull inward. Resisting this is the energy from fusion, pushing outward as radiation tries to escape. These two forces maintain equilibrium, neither ever winning. This balance means stars can only exist within a certain size range. At the small end are red dwarfs, stars so small and dim their light is mostly infrared. The smallest known star is EBLM J500 and 5557 Ob, about 600 light-years away. It is only about 88 times Jupiter's mass, right at the limit. Any smaller, and gravity would be too weak to ignite fusion. It's less than 1/10 of the sun's mass and has a radius similar to Saturn's. Smaller still are brown dwarfs, hybrid objects between planets and stars. They briefly fuse deuterium after formation, then cool off. Red dwarfs are the most common stars, making up about 2/3 of the Milky Way's stellar population. Our nearest stellar neighbor, Proxima Centauri, is a red dwarf, too dim to see with the naked eye. At the other end are the true giants. The largest stars are so big their true extent is hard to measure. Their surfaces are bloated and in constant flux, swelling and contracting violently. Their brightness changes over days, making precise measurement difficult. For the most massive, luminous, and hottest known star, analogy fails. R136 Aeon, located 136,000 light-years away in the Large Magellanic Cloud, weighs nearly 300 times the Sun's mass and outshines 1,000,000 suns. It's so hot most of its output is ultraviolet. To the naked eye, it is only 164,000 times brighter than the Sun. At the distance of Proxima Centauri, it would outshine the full moon. R136 Aeon sits at the limit of stellar mass. Heavier stars have greater gravitational pressure in their cores, leading to higher fusion rates, more radiation, and more energy poured into the star. Above 300 solar masses, a star's core would produce so much radiation it would blow itself apart in a fury akin to a supernova at birth. This is the limit for modern stars, which contain traces of elements heavier than hydrogen and helium that absorb light and affect the balance. In the early universe, the first stars had no such limits and may have swelled to 10,000 solar masses or more. Only two kinds of objects in a galaxy are larger than stars, representing the start and end stages of the dance between radiation and gravity. Stars form from giant molecular clouds, vast complexes of gas and dust drifting through the galaxy, barely held together by their own gravity. If you found this exploration of scales, from the quantum foam to the vastness of stars, fascinating, please show your support. Liking this video helps others discover it, and subscribing ensures you won't miss our next journey into the universe's wonders. If you know someone who would love this content, please share it with them. Thank you for watching TS heavier than hydrogen and helium that absorb light and affect the balance. In the early universe, the first stars had no such limits and may have swelled to 10,000 solar masses or more. Only two kinds of objects in a galaxy are larger than stars, representing the start and end stages of the dance between radiation and gravity. Stars form from giant molecular clouds, vast complexes of gas and dust drifting through the galaxy, barely held together by their own gravity. If you found this exploration of scales, from the quantum foam to the vastness of stars, fascinating, please show your support. Liking this video helps others discover it, and subscribing ensures you won't miss our next journey into the universe's wonders. If you know someone who would love this content, please share it with them. Thank you for watching.